Hello to all my geometry friends. Today we are going to look at the Pythagorean Theorem. The Pythagorean Theorem is almost certainly the most well-known theorem in geometry and perhaps in mathematics in general. It is a powerful theorem and it is not difficult to demonstrate. So let's take a look.
Mr. Wade, are we going to do a formal proof?
Excellent question, Zorg. We are not going to write a formal proof, but we are going to demonstrate why the theorem is true using properties of both geometry and algebra. Writing it out as a formal proof is more time-consuming and we will do that later. However, this demonstration could be easily written out as a proof. So let's get started. For this demonstration, it will be helpful to remember the definition of triangle congruence and the properties of triangles and quadrilaterals. Zappo. We will start with a square. Let's call it square A, B, C, D. We start with a square because it has 4 congruent sides and 4 right angles. On side A, B, we pick a point and label it E. Then we locate points F on side B, C, so that segment B, F is congruent to segment A, E. We continue the same process for the remaining sides.
So Mr. Wade, am I correct in concluding that the segments in blue are also congruent by using segment subtraction?
Brilliant, Zorg.
Thanks.
Let's mark the figure. Now let's connect the 4 new points with segments. We now have a new quadrilateral, E, F, G, H and 4 right triangles. Do you see them, Zorg?
Yes, I do.
What do we know about the right triangles?
They are all congruent by the side, angle, side, postulate for triangle congruence.
Brilliant once again. Now, by the definition of congruent triangles, what folks often call C, P, C, T, C, we get the sides of the inscribed quadrilateral to be congruent as well as the corresponding acute angles of the right triangles. Let's highlight the triangles. Now, what do you know about the acute angles of a right triangle, Zorg?
They are complementary.
Correct. And so, angles 1 and 2 are complementary, and since angles 2 and 3 are congruent, we can say that angles 1 and 3 are complementary as well. Since angles 1, 3 and 4 form a line, we know they are to 180 degrees. We can subtract the measures of angle 1 and angle 3 and be left with 90 degrees for angle 4. The same logic applies to the other 3 angles of the inscribed quadrilateral, and so we can conclude that it is a
square.
Raise your hand please, Zorg. But you are correct, it is a square. I made a copy of one of the right triangles and put it to the side. I have labeled the segments in the figure so that the short blue segments have a measure of A, the medium red segments have a measure of B, and the sides of the inscribed square, which are also the hypotenuses of the right triangles, have a measure of C. Now we will calculate the area of the big square using 2 different methods. Can you think of 2 ways to do that, Zorg?
Yes, we can use the formula for the area of a square, side squared, and use A plus B as the side length. Or, we can add the areas of the 4 right triangles to the area of the inscribed square.
Brilliant again, Zorg. Let's look at how that will work. First, the area by adding. The area of the right triangles is 1/2 A times B. There are 4 of them, so it's 4 times the quantity 1/2 A times B, which simplifies to 2B, A. Then add the C squared for the inscribed square. That area is equal to the square of the sum A plus B, which simplifies to A squared plus 2A, B plus B squared. We set those areas equal to each other and then subtract the common value of 2A, B, and bingo. A squared plus B squared equals C squared.
So, the sum of the squares of the lengths of the legs of a right triangle is equal to the square of the length of the hypotenuse.
Correct. Remember, if we state it as A squared plus B squared equals C squared, we must remember to identify what A, B, and C represent.